it hit us. On December 27, 2004, radiation from a dead star reached Earth from the far side of the Milky Way. You didn't feel it. Nobody looked up. There was no explosion in the sky. But satellites were saturated. Gamma-ray detectors were blinded. Earth's upper atmosphere was disturbed by something that happened 50,000 light-years away. In roughly the time it takes to blink, that dead star released as much energy as our sun produces in hundreds of thousands of years. The source was only about 20 kilometers wide, smaller than a city, denser than an atomic nucleus, and its magnetic field was so strong that close to it, chemistry stops behaving like chemistry. This is a magnetar, and it is not just another extreme object in space. It is one of the few things in the universe that can reach across the galaxy and physically touch a planet. So what happened in 2004? Why did almost no one notice? And how close would a magnetar need to be before Earth stopped being safe? A magnetar begins with the death of a massive star.
When a star many times heavier than the Sun runs out of fuel, its core collapses. The outer layers explode outward in a supernova. The center gets crushed into something almost impossible, a neutron star. Imagine taking more mass than the Sun and squeezing it into a sphere the size of a city. A teaspoon of that matter would weigh hundreds of millions to billions of tons, depending on how you measure it. Most neutron stars become pulsars, spinning cosmic lighthouses that sweep beams of radiation through space. But some are born with magnetic fields far beyond ordinary neutron stars. During collapse, rotation and turbulence can amplify the field to absurd levels. The result is a magnetar, a dead star whose magnetic field is the main engine of its violence. And that is what makes magnetars different from the other monsters in astronomy. A black hole is terrifying because it hides behind a boundary. Cross the event horizon and the universe has no way to return your signal.
But a magnetar does not need you to fall into it. It broadcasts its danger outward. Its magnetic field twists through space. Its crust stores stress. Its flares move at the speed of light. Imagine a corpse that can still scream so loudly the echo changes the edge of a planet. That is the category SGR 1806-20 belongs to. The object that hit us in 2004 was called SGR 1806-20. It did not explode like a normal star. It cracked. A magnetar has a crust, not rock, but nuclear matter locked under gravity hundreds of billions of times stronger than Earth's. Beneath and around that crust, the magnetic field twists, strains, and stores energy. Eventually, the crust gives way. That is a starquake. On Earth, a magnitude 9.5 earthquake is one of the most violent events we have ever measured. On a magnetar, the numbers leave normal language behind. Some estimates put the 2004 starquake at an equivalent magnitude around 32, not because it is the same kind of earthquake, but because the energy scale is almost meaningless by human standards.
The burst crossed the galaxy for tens of thousands of years. Then, on one ordinary December day, it arrived. For a fraction of a second, Earth was inside the flash. And the most disturbing part is that the earthquake was not even the main reason magnetars are terrifying. Earth's magnetic field, is about 50 microtesla, enough to turn a compass needle. A hospital MRI is around 1 to 3 Tesla, strong enough that metal objects become dangerous. The strongest continuous magnets built in laboratories are measured in tens of Tesla. An ordinary neutron star can reach around 100 million Tesla. A magnetar can reach 100 billion Tesla. That is not a bigger magnet in the everyday sense. It is a different physical environment. At magnetar-level fields, atoms are distorted. Electron clouds get stretched along the direction of the magnetic field. Chemical bonds no longer behave the way they do on Earth. Water, proteins, DNA, the shapes that let biology exist, all of them depend on ordinary chemistry. A strong enough magnetic field does not need to burn you or crush you first. It can make the rules that hold molecules together stop being familiar. This is why the best description of a magnetar is not a powerful magnet. It is a place where chemistry loses. The nearest known magnetar is about 9,000 light-years away. That is safely far.
But known is doing a lot of work. Magnetars are easiest to find when they are active, when they flare, burst, pulse, or scream in X-rays and gamma rays. Their active phase may last only around 10,000 years. After that, they can fade into the dark population of neutron stars. So the real question is not whether the known magnetars are close. The real question is what a close one would do. Within roughly 1,000 kilometers, the magnetic field itself would be lethal. Not because it pulls iron out of your blood like a cartoon magnet, but because fields in that regime can distort the electron structures that chemistry depends on. Before you worried about radiation, gravity, or heat, biology would already be impossible. Farther out, the danger changes. The magnetic field weakens with distance, but giant flares still matter. The 2004 event showed that a single magnetar flare can disturb Earth from galactic distances. If a flare like SGR 1806-20 happened within about 10 light-years, several sources estimate it could damage or destroy the ozone layer and trigger a mass extinction-level event.
10 light-years is enormous by human standards. In galactic terms, it is next door. There are only about 30 confirmed magnetars in the Milky Way. 30, in a galaxy with hundreds of billions of stars. That sounds comforting until you remember that astronomy does not count what it cannot see. A magnetar that has gone quiet is hard to identify. It may no longer flare. It may no longer shout in gamma rays. It may just drift through the galaxy as a dark neutron star, carrying the remains of a magnetic field that was once monstrous. So when we say no dangerous magnetar is near Earth, what we really mean is this: no active, detected magnetar is near Earth. That is still good news, but it is not the same sentence. And that difference matters because magnetars are temporary monsters. For a short time, they are some of the loudest objects in the high-energy sky. They burst, they flare, they announce themselves. But then, the violence fades. The star cools. The magnetic field decays. The screaming object becomes a quiet corpse among countless other dead stars. If one of those old magnetars passed between bright, active phases, it would not look like the villain of a science fiction story. It would look like almost nothing. And then, magnetars gave astronomers another reason to care about them, because they may not just explain one terrifying event in 2004. They may explain one of the strangest signals ever detected from deep space. For years, Astronomers were chasing fast radio bursts. They are extremely short pulses of radio energy, milliseconds long, often coming from far outside our galaxy. Some release as much energy in a blink as the sun emits over days. The problem was simple. Nobody knew what made them. Black holes, neutron stars, collisions, something completely new. Then on April 28, 2020, a magnetar in our own galaxy changed the conversation. SGR 1935 plus 2154 produced a burst of radio energy detected by instruments on Earth. It was not as powerful as the most distant fast radio bursts, but it was the first time a radio burst like this was tied directly to a known source. And the source was a magnetar. In one moment, magnetars went from rare cosmic nightmares to leading suspects in one of the biggest mysteries in modern astronomy. Not all fast radio bursts have to come from magnetars, but at least one did. And that was enough to change the field. Because the terrifying thing about fast radio bursts is not just their power. It is their cleanliness.
A signal appears. It lasts milliseconds. Then it is gone. No slow explosion, no long warning. Just a needle of energy crossing the universe and landing inside a telescope. For years, that made them feel almost artificial. Not because they were artificial, but because nature rarely gives us anything so sharp. Then, a magnetar did it. Not perfectly, not with every mystery solved, but enough to prove that a dead star with a twisted magnetic field can produce one of the cleanest, strangest signals in astronomy. Then came SN 2024 AFAV. In late 2024, astronomers detected a superluminous supernova roughly 1 billion light-years away. It was brighter than ordinary stellar explosions, and more importantly, it flickered in a strange repeating pattern. Over months of observation, the light curve showed 4 distinct bumps. Each one arrived faster than the last, like a chirp. In 2026, Joseph Farah and collaborators published an explanation in Nature. The signal could be produced by a newborn magnetar surrounded by a tilted disk of fallback material. As the spinning magnetar dragged space-time around it, the disk processed through the lens-thirring effect, periodically changing what we saw.
The model pointed to a neutron star spinning every 4.2 milliseconds, with a magnetic field hundreds of trillions of times stronger than Earth's. For the first time, astronomers had evidence of a magnetar being born inside a supernova. We had seen magnetars flare. We had seen them solve a radio mystery. Now, we may have watched one come into existence. A dead star only 20 kilometers wide reached across the galaxy and touched our atmosphere. Another helped explain radio flashes from deep space. Another may have announced its own birth through a chirp in the light of a supernova. Magnetars are rare, brief, violent, and most of them may spend almost all of cosmic history invisible. That is the real horror of them. Not that one is coming for us, but that the universe contains objects this extreme, this small, this quiet, and this capable of changing a planet from tens of thousands of light years away. And next, the mystery gets stranger, because some stars do not explode. They do not flare. They simply dim, again and again, as if something enormous is passing in front of them.
Next video, Tabby's star.
The object that made astronomers ask whether a civilization could build a shadow large enough to be seen from Earth.